Welcome everybody to Simplified. My name is Michael.
And I am Gurjit.
This is episode 9.
So, as I said, I'm going to tell a little bit more about what makes the thing a little more exciting and why I do what I do. And as I said, this is like the role of science and scientists to investigate something that's interesting and also have fun. Mm-hmm. So what always attracted me about the universe in general is the different pictures that we have of the universe. When you take, for instance, a photograph of the universe with big telescopes, for instance, or with a Hubble Space Telescope, mm-hmm. What do you see? You see a collection of little islands of light that we call galaxies.
Yes.
Where there are stars. Okay, and these things look like an empty space. Everything is black, and then you have these little galaxies, and they're very small compared to the size of the universe. But actually, when you do a simulation or a model of the universe, when you consider all the matter that should be in the universe, then our theory predicts that those little things that we call galaxy should be completely insignificant, because most of the matter in the universe should be outside of them.
What do you mean? Like between the galaxies, you'd have
between the galaxies, yes.
It's the dark stuff in which we can see the galaxies. Most of the matter lies in the dark stuff.
The point is that what you see with the telescope is only the stars. Mm-hmm. But when you count how much matter there should be in the universe, the star count for less than 1%, much less than 1%.
Wow. Okay.
And actually, we think that most of the matter in the universe should be in a form that we actually don't know what it's made of, and we call it the dark matter.
Yes. Because so you don't see it. Can you?
We don't see it with our telescopes. Yeah.
But we know it is there because it has matter, and we can see it in our simulations. That
we can also probe it gravitationally, for instance.
So galaxies are connected with these filaments.
Filaments,
yes,
that are mostly made of dark matter and hydrogen and helium photons, but with no stars between. And as I said, one possible example to sort of visualize this is like neurons in our brain that are connected by these filaments.
Yeah, so it's basic. By neurons, you mean the neuron head would be the galaxy, and then the string.
Yeah, you have to imagine the galaxy are in the densest part of these filaments, where the filaments are connected to each other. But most of the matter should be in between them. And as I said, this is all in our head, in our model, and we think that this model is pretty established.
Yes.
It just comes from the initial condition of the universe, just using Newton's law. So it should also be something very. We don't know the nature of dark matter, but we know how gravitation works.
Yes.
We think. And so my focus, my goal since the beginning of my PhD was to try to connect these two things. Our picture of the universe we have from the stars, from the galaxies, and our picture we have from the gravitationally dominant component. Mm-hmm. And how to do this? Well, I thought it would be very nice if we can really take a picture of these filaments, of this network of things, and
but
really
can't see it.
Well, you have to think about how can we see it. So definitely we cannot see the dark matter directly, because dark matter doesn't emit electromagnetic radiation.
Yes.
At least we think it does not emit light. But as I said, in these dark matter filaments, there is also some atoms of hydrogen. Very few of them, but there are there. And hydrogen, it emits light.
Yes.
For instance, I usually give as an example, think about the Orion Nebula. The Orion Nebula is just gas. It's just made of gas. Mm-hmm. And what's the reason why you are seeing this nebula there? The reason why you see the nebula is because there are some little stars inside it that are emitting a lot of photons, very bright UV photons. And these UV photons are enough to make all this gas to glow. And what's this mechanism? It's like fluorescence. Indeed, I call it fluorescence. It's that some gas that is emitting light because it's illuminated by some UV sources, like the normal fluorescence thing. It doesn't emit light by itself, but because it's illuminated by a UV source. Now, it works in our galaxy. Imagine the Orion Nebula, it's a large thing, you have small stars. Imagine now, and this is the size of, I don't know, few light years. Okay? Imagine that you want to now to illuminate the cosmic web of the universe on size of millions of light years. What do you need? You need something that is a million times brighter than the star in our galaxy is.
Yes.
And luckily, we have something that is as bright in the universe. And these things are called quasars.
I'm sorry?
Quasars.
Quasars.
Now,
Q-U-A-S-A.
Yeah, these things are funny things because if I tell you what a quasar is, you say, wow, it's weird. The quasar, we think, are black holes, are extremely massive black holes, like as massive as a little galaxy, like a million or a billion of masses of our sun.
Wow, okay. Wow.
But this is black. It's black hole. Doesn't mean radiation by itself. But around this black hole, we think there is some accretion disk. There is a disk of matter, and this is what is emitting a lot of UV radiation.
Why? Does it densify the matter around the edge of the black hole?
Yeah, the matter is accreting into the black hole, and in the process of accretion, it produces all this radiation.
Oh, and that enables you to see it.
And that's enabled to, and actually these things are the brightest things in the universe,
Wow.
you can see. They look like the little stars. They are like little dots.
Mm-hmm.
That's the reason why they're called quasar. Quasar means a quasi-star. And until like the middle of last century, people thought they were actually stars. And then we discovered they're actually a very distant object. And by the virtue of being very distant and very bright, that means they're very intrinsically bright. So now the sort of trick is to use these quasars as a sort of flashlight to make this very faint hydrogen nebulosity, this gas, to glow in the universe. Mm-hmm. So you have to imagine like you have this very bright flashlight that is illuminating some part of it.
Yes. Is it like sending out radiation all around and then?
Yeah, we actually think that the quasar don't send radiation all like a light bulb. More like a flashlight. It's like pointing in one particular direction.
And
that's our.
So this kind of gives you like a area to look at more.
Yeah. So
accurately.
We actually think that because we see the quasar, we are in the flashlight beam.
Yes.
That's what we think.
That makes sense.
But we also think, like in some cases, this is like a separate argument. I think it's fun anyway. That sometimes we also see quasar where the flashlight beam is pointing in a different direction with respect to us, and they look different. But anyway, if we have a very bright quasar, a very bright flashlight, then we can do the experiment and look around it. So, for which kind of emission we look like, as I said, we look for a reprocessed emission that we call fluorescent emission. Mm-hmm. And in particular, we look at emission from hydrogen gas and a transition that is the brightest line of hydrogen gas. That typically is in the UV, so it's not visible. It has a wavelength of around 1000 angstrom. It's called Raman alpha. But because we are looking in a very distant universe, we can actually see this emission Doppler shifted into the optical.
Yes.
And so the idea is to then look into the optical radiation around the quasar for that particular emission line. Okay? And so how do we do this in practice? So imagine that you have to take a picture of the Orion Nebula or whatever. The Orion Nebula also has this gas emission transition. An amateur astronomer photographer will tell you, well, the best way is to use a filter.
Yes.
Take a filter that specific wavelength, and that will make it brighter.
Mm-hmm.
That's also what people do. They use filters to make things brighter if the wavelength of emission is in one particular filter.
So it just filters out all the other wavelengths, basically.
Yeah, it's like an optical filter that is only selecting a part of the wavelength or a given color. Okay? And so we do the same thing. So we build like filters, optical filters, to select that particular line, that particular color. The color was around bluish or violet color, and put this filter on the largest telescope in the world.
Yes.
Like on the very large telescope in Paranal or at the Keck telescope at Hawaii. I've been doing experiments with those. And then take a picture like as long as 4 nights.
Wow. So what you
It's a very big picture.
These are just huge optical telescopes.
Yes, it's
And
like the size of the mirror is around, it's like 8 meters.
Okay. Wow.
So it's not like, I'm doing an example of a camera of an amateur astronomer. This is like huge things. So the filter itself, I think, was as large as maybe 20 or 30 centimeter. And actually didn't cost much, but in relative terms.
Yeah.
Is it literally just a sheet of plastic?
It's not actually plastic. It's made of, it's called an interference filter. So it's made with several layers of material, very closely packed. And actually the way in which these things are arranged with each other, it creates interference in such a way that you only have some particular wavelengths that can go through, and all the rest get out.
Wow, okay.
Yeah, these are also used by amateur astronomer, and this is called interference filter. Yeah.
So this is just on a larger scale.
Yeah, well, I have to say it's a little bit more precise than a normal filter that you can use on camera.
It's just better quality.
It's better quality, yes. Better quality and better control exactly of what the color you are selecting. And then we just took very long pictures. And the idea was to see anything that was light up by this quasar. And we were very lucky, because the first night we took an image at the Keck telescope, we indeed found a huge filament that was emitting in this Lama alpha emission. And by huge, I mean several million light years of size. Okay. So 1,000 or 1,000,000 times larger than a single galaxy. So really something that's huge. I mean, that cannot be associated with individual galaxies, but really with this gas that is in between them.
And this filament was lit up by these quasar flashlights.
We think that that was lit up by this quasar, because the quasar is right there at the center of it. And typically, when you see these discoveries, when you read them in the newspaper, you always see like a number associated with a quasar or whatever, like a telephone number or a zip code or whatever. But I can never remember telephone numbers. And actually, the nebulae in our galaxy, they have names.
Yes.
Like the Orion Nebula, the Horseshoe Nebula, or whatever they are called, like the Crab Nebula. Because historically, the people give names to things. So I thought to give a name as well to the nebula.
Yes.
And because I was in Santa Cruz, and the mascot of Santa Cruz is a banana slug, and the nebula looks like a slug, then the nebula was named the Slug Nebula.
Slug Nebula.
Awesome.
I have to say that unfortunately, we published this result in Nature, but the editor of Nature didn't like the name.
Oh,
so in the Nature paper, you can actually find the zip code of the quasar.
So this is quasar 1547 something like that.
Yeah, actually the name of the quasar is like UM287.
Ah.
I remember by now. It's a very short number.
Slug sounds so much nicer.
But all in the rest on the web and in the subsequent papers we were called like the Slug Nebula. And I think this was one of the most exciting discoveries that we made, because you can imagine after so many years you work on a project, then you build filter, and then you go to telescope. It's a very long process, and in the end, it's like it's a discovery. You don't know if you're going to find something.
Yeah,
it's all exploratory.
It's exploratory, yes.
Yeah.
You don't know, And many times, I mean, before that, we didn't see anything. So you have to just be sort of perseverant and keep trying it. And so that was a very exciting moment, I have to say.
It must have been really amazing that you've been building this up, and in one night suddenly you see this.
Yeah, I mean, I was lucky because it was the first night it has been after 20 years. Indeed, when we looked for other quasars using these filters, we didn't see any other huge nebula.
Mm-hmm.
We only found like 2 of this over like 20 quasars that we observed using this technique. And so why this thing is interesting? You say, yeah, you found a filament, so what can we do with it?
So from what I get, does it in a way give us more proof about the theory of dark matter existing?
Yeah, well, first of all, it looks like a filament. That is something like interesting because we didn't really have a picture of these things before. Mm-hmm. We always imagined like it should be like filamentary, but actually, until you see it, it looks like a filament. It's like sort of fat filament though, and we think this is because this quasar is living in a very it's a very rare object in the universe, so it's probably has a very massive galaxy associated to it. So, but the sort of important thing is that with the emission we can detect, we can actually measure the densities of the gas. And what we actually found is that what we are measuring doesn't correspond to our expectations. What we were expecting from the theory or the simulations. And that's, I think, is the most interesting part of the game, because it's only when what you're finding is challenging your previous expectation that you have an opportunity to learn new things.
Yes.
If you find what you expect, then it's done.
It's just proving kind of what
you're proving, but then there is nothing. I mean, it's not fun anymore. but if what you find doesn't correspond to what you were expecting, then you have an opportunity to learn new things. And that was indeed this case, because the densities that we're finding are much higher than what we were expecting from our theory. Mm. And so we think that actually the way in which the matter is distributed in this filament, it's not in a uniform way, but more like in a very clumpy and dishomogeneous or inhomogeneous way, like in a very small thing. Mm-hmm. And this might tell us more about how the cosmic structure form and evolve, and maybe also about the nature of dark matter that is providing the gravitational wells,
yes,
where these things are maybe collapsing. And indeed, now we are studying, we are also investigating from the theoretical point of view how this thing can form. So the nice part, as you heard, is like this is an observational project, but I like to do also the theoretical numerical part. Mm-hmm. And we do this thing together. So we now try to improve our theory because we have now this new data. And this is actually what often happens in science. Until you have the data, in most cases you're not really advancing much in the theoretical part. It's only when you have some new data then you have like sudden a new way in which you can advance your theoretical understanding. In some cases the opposite. There is some theory predicting something, nobody can observe it, and then stays there for a very long time, and then suddenly you get a jump. But in this case it was really like the data and the observation is driving a new way, a new theoretical way in which we are looking at the cosmic structure formation. So this is what happened with this technique that we were using filters. And then why I'm back here at ETH is because ETH is part of a big consortium that built a completely new instrument for this telescope that is based on a new idea. And the idea is that you don't just take images or you take spectra or a given wavelength, but this instrument is able to give you like an image at each wavelength.
Okay.
So it doesn't give you like a single image, it gives you like a cube.
Yes.
Does it capture just several wavelengths?
Several wavelengths, yes, at once. This is called the integral field spectroscopy.
Okay.
And this is a completely unique instrument because it has a very large view. I mean, you can really sample a large part of the universe, and before these things were extremely small. You can barely see a galaxy at the time, but with this thing we can actually see much larger scales, on the scales of these filaments, for instance. And so now, instead of building filters, we can just use this instrument, and if there is anything at a given color or wavelength, then we're going to see it. And indeed, with the first experiment that we did with this instrument, revealed that actually when you look around quasar, each quasar is surrounded by these giant filaments and nebulae. Just before we're not able to see them, probably using our previous technique. So here again, an advancement in technique is giving us even more data, more unexpected than we were thinking before.
You mean before you chose this one wavelength based on theory?
Exactly. Based on a particular quasar.
Based on, okay.
So you have to imagine this quasar are very, very, very far away in the universe. The universe is expanding, and while the universe is expanding, the color of the light, the wavelength of the light that is emitted is stretched.
Mm-hmm.
It's a sort of Doppler effect. And so more far away you look in the universe, and more the light is stretched towards the red.
It's the redshift.
Yeah, we call this redshift. If you know the redshift of the quasar, so what we did in the past is to build a filter exactly of the color that corresponds to the redshift of that particular quasar. But you can do like 1 or 2 quasars at a time in this way.
Yeah.
That was limiting us. Now with this new instrument, we can actually do many more quasars, because we don't have to build filters anymore. We can just look at each wavelength and search for this nebulae or filaments. Yeah. And this is really like something that was published recently last year here at ETH. And we're also very proud of that, because it's this instrument took a very long time to be developed, like more than 10 years, I would say. And so after all this efforts into the instrument, and making these discoveries is something also very exciting and rewarding, I have to say. And so now we are in the process of taking more data and more observation, and at the same time to advance our understanding. But for us, it's a completely new window in the way in which we can look at the distant universe and how things form and evolve in between galaxies rather than just on the galaxy levels.
And what's your overall goal for this? Is it to create a good map of the cosmic web?
Our overall goal is really to understand how structure forms in the universe, from the largest scales to the smallest. So one thing I didn't mention is that why this gas in between galaxies is important. It's not just some gas that is sitting there. This gas is actually the fuel for the galaxies to form the stars. You have to imagine the galaxies are consuming their gas to form stars. And so in order to keep them activity alive, to be like they are today, they continuously need to get this fuel from the outside. And so we think that this gas is actually coming from the outside and is fueling the galaxies.
Is this gas just spread across the galaxies?
Yeah, in the filament. So you have to imagine this gas is flowing towards the filament, and it's actually forming the galaxies.
Wow.
And the galaxies are consuming their fuel forming stars. And if there will be no other flow of gas through this galaxy, they will just become dead with no stars forming anymore. But actually, we think this gas is continuously flowing and forming galaxies. So understanding what's around galaxies helps us to understand also how galaxies form and evolve. So this is one of the goals. And if you have a lot of gas, dense gas, this change the picture in which the galaxies form. And second, and I think this is also a very important goal for me, is really to understand what is the nature of this material that is outside of the galaxies, and what does it tell us about the dark matter, for instance. Mm-hmm. If this gas is in very little clumps or in more uniform distribution, this may be related on the physical properties of the dark matter. And at the moment, the only information we have of the dark matter is on different scales than this that we can prove. And maybe one day also, thanks to this observation, we can really constrain what this dark matter is and give it a name to it. At the moment, we don't know yet, so we'll probably keep dark matter because we're used to that. But
So on a purely speculative manner from here, because we have so many questions to still answer, what do you think? What is your hunch about what is dark matter?
well, me personally, I mean, probably this is a question that should be addressed to a particle physicist, because the particle physicists are looking for this particle. So the mysterious thing is that it should be something outside of our standard model.
Mm-hmm.
So it's clear that what our observation, what astrophysicists is telling us is that there is something that is beyond that. And once again, if you have something that doesn't meet your expectation, you have the possibility to learn some completely new physics. So I think this is really like the challenge for physics of this century. Not just to say what dark matter is, but to come up with a new model for our understanding of particle physics. And this is something that will take a big effort, not just on the astrophysical side, but on all branches of theoretical physics. So, if you ask me, it's different. I will not put any guess on that
Okay.
at the moment, but yeah, something very exciting, and that will keep us going, I think, for a long time.
That was one of. Is that your main focus? Clearly, or is there some? Because you said you also do simulations for these things. Do you have a subsidiary focus?
Yeah, this is the main focus, because it's like a big goal. But we're also interested in how galaxies in particular are forming. Mm-hmm. So now I tell you before you have these filaments, but at a certain point these filaments should become dense enough to become galaxies. And the question is how galaxies become galaxies. Is there a phase in which you have a lot of gas but no stars? And we call this phase like the dark galaxy phase. So we're also looking for dark galaxies. And so we're trying to understand how you can go from these filaments into forming a galaxy. So that's more on the scale of individual galaxies. And then, again, try to understand how this galaxy then will get the fuel from the outside. And once again, we're doing this using observation, particularly observation again using the same technique but focusing on very small things rather than big filaments, and doing numerical simulations as well of galaxy formation.
That's good. Onto a more personal question. What brought you to this field and to eventually become a professor as well?
Curiosity. Since I was a child, I was never sort of satisfied with what I see just around me. I said there's so much outside of this little place, and I just look above me and I saw this whole universe to explore. So it's just curiosity. It's just the sort of need for exploration. Mm-hmm. And so what brought me on the distant universe is the fact that it's so far away and so large, and so dark in a sense that there's a lot of space for satisfying my curiosity and my need for exploration. Mm-hmm. So just this. So professor was never professor is a phase of a career of a scientist that which you have to go, because you cannot always stay a student or a postdoc, and it comes with different responsibilities, with different duties. Mm-hmm. And so in my previous life, I was mostly focusing on my own research, on satisfying my curiosity, on really get the best I could do from that. And now as a professor, I am switching a bit roles and actually helping others to fulfill their dreams. The students and the postdoc, and indeed I spend most of the time helping the others.
So what advice would you give to young people trying to satisfy their curiosity?
Yeah, I would say I think it's important to be driven by your own personal curiosity, and questions. Many students or people come to me and ask me about what are the job possibility afterwards, the potential address. And well, I think if you want to become an astronomer, you don't really have to think about that. If you want money or job, there are so many other jobs that can give you that. What can astronomy and science can give you? It can give you the thrill to make discoveries and satisfy your curiosity. And so that should be the driving part of doing this job. Otherwise, there's no point. We are not rich. We don't have extra vacation. We actually sometimes we have to do a lot of sacrifice. We have to work at night at telescopes.
Oh
Yes.
Sometimes we have to work during the weekends as well, because you have to have something to really that is driving you, and so it's a sort of bit of sacrifice on the other aspect of life. We don't have office hours, like 8 to 5, and then you go home, because if you're really driven by this, you really work on this, and this is the nice part of it, but this is also the part that is different from other jobs. So my suggestion that I give is if you really want to do this, then be driven by your main goal of being a scientist.
That's great. One last question we'll ask you, which is kind of like a pet question that we ask everyone we interview. What's on your bookmarks bar?
I can tell you, I have no bookmark.
You don't have bookmarks? you are the second person we've spoken to so far who have either no or very few bookmarks.
I was used to have those, but then I don't use them anymore. The few websites I use, I just type on the Google bar the first 3 letters.
Yeah, it just shows
appear.
up. Yeah.
So it's probably because now with the new browser, you don't need that bookmark anymore, and you just need to type the first 3 letters. If it is a very frequently used site,
Yeah. Then it just shows
type
up.
one letter.
Yeah.
And then so I think it's the fastest thing. I think it's just practical. It's not really because I don't have site where I go frequently. It's just because you don't need that anymore. Just type 3 letters and then it's there. It's faster than going on the thing. So what are the most frequently cited? So every day I go on a page. It's called the archive, Astro page, where there are pre-prints every day. So that's that's my daily routine. I started that and look at the papers and
Keeps you updated with what's going on right now.
And actually, we have every day here at 12 a meeting where we discuss these papers. From
Every day?
Every day.
Wow.
Okay. Usually it's once a week in groups.
Yeah. I have to say, not every day we have very good people to discuss. But in some cases, we also have longer meetings.
Thank you so much, Professor Cantalupo, for your time. This was really interesting, and the way you explained these things is really amazing. Thank you so much.
I'm glad that you liked it.
Thank you for listening. If you liked it, we'd really appreciate it if you shared it and gave us your feedback. We publish a new episode every week. For more details, visit our website simplified.xyz.